In the previous video, we created a breakpoint struct and a data structure around it, that is the stop point collection. And then we added the collection to our process struct. The breakpoint is applied on virtual addresses, as you can see right here. And now we need to figure out how to actually find out this virtual address on which we need to apply the breakpoint. To do that, we will be using the obj dump command, and it is already available on your WSL. It may not be if you are working on Linux. I don't know, maybe you need to install it, sudo apt-get or something. So I'll leave that up to you. But before we use that command, we need to first write a program on which we will apply the breakpoints, right? We need to figure out these virtual addresses, but for what? For a program, right? So we first need to create that. So what I'll do is I will create, wait. So ls cd tests ls. So we have the test process.c right here, right? So we will also create another code file, a program, and we will apply the breakpoints on that program. All right, so let's create a printer dot cpp. We will just be printing some numbers in here. So I'll copy and paste some code for you, and it's just basic C++ code. We are including standard output, and then we are printing 1, 2, and 3 in here. Right, we can quit, and now we will compile it. But we will compile it with a particular command. We will use certain flags for it, and I'll tell you soon why. So I want you to use this command gcc, and these flags. What's the error? Extended is not valid in an identifier. I guess there is some issue with me printing, so when you copy pasting. So let's just write it. Hash include cstdio, and then int main std puts two and 3. Right quit. Let's try to compile it again, and this time it works fine. So the issue was in printing. And let me remove the binaries, test process and printer and hello 2. So these should be the only 3 files in here. And now let's compile it again. So I want you to use this command, and we need these flags in this command because we will be working on binaries with relative addresses. And that's because all the modern compilers, the GCC compiler and all the other compilers that you're going to use, they would compile the code down to a binary, and the binary would be using the virtual relative addresses. All right, it won't be the absolute address that we need for the debugger. That's the modern standard, and we also want to disable all compiler optimization. So what the C++ compiler does is, if the for loop can be removed deterministically, if you're running a for loop for 1 to 5 and you're just adding 1, 2, 3, 4, 5 to a variable, the GCC compiler will remove that for loop for you. It will automatically do that. It will deterministically calculate that number at compile time itself. So we want to disable that because we want to apply breakpoints on that for loop maybe. All right. What I mean to say is, let me show that to you. So if you create int I equal to 0 and then you run a for loop here, j less than equal to 5, j plus plus, and I plus is equal to j. If you write this and compile it normally, the GCC compiler will remove this for loop, and it will calculate the value of I and put the value of I, this for loop will be removed. But we don't want that because we want to be able to apply breakpoints in this for loop. So we want to disable all the compiler optimizations. And we also want, what this command does is, what this command also does is, it compiles the binary with debug information, and that will be useful later on. We need the debug information about the program. Now that we have the binary right here, printer, we can use the obj dump command on it. The obj dump command will give you the memory address of binary instructions. So when you compile the code, it is converted into binary instructions. So what this command will do is, it will give you a disassembled representation of those binary instructions. It will be better to just see what it does. Obj dump -s and then printer. As you can see, this is the main function, and it gives you this binary. This is the disassembled assembly code, right? So this obj dump command, it disassembles the binary into assembly code, and then it gives you the memory addresses as well. So these memory addresses that you see right here, these are relative addresses. What that means is, these are just offsets from where the binary is loaded into memory. If the binary is loaded at memory address 1000, then this line is at 1149. Since it's a relative address, this is actually at 1000 plus 1149, because it's a relative address, not the absolute address. That's what the relative address means. All right. Looking at this code, we should have 3 print statements. We have them right here, std puts, but this line is actually called right here. You can see the assembly code call. This is the actual line that is calling this function. So it is at memory address 115b. Similarly, we have we have another 116a, and the third one is at 1179. These are the three addresses on which we should try to apply the breakpoints and stop the control execution. So if I apply the breakpoint at this line right here, I expect when I run this code, I expect it to not print 1. And when I continue, I expect it to print just 1 and then stop right here. And then when I continue again, I expect it to print 2 and then it should stop right here. And then when I continue again, I expect it to print 3 and then exit, because we don't have any breakpoint after that. As I told you, these are relative addresses, so we can't use these memory addresses that you see right here, given by these tools, given by this tool. That is because the binary is not necessarily loaded at memory location 00. If it were, then these memory addresses would work fine, but that's not the case. This binary can be loaded into anywhere in the memory, in the RAM, and then we expect it to work fine. So these are the relative addresses. To actually figure out the final real memory address, we need to inspect the address space of the process. So when the process is already loaded into memory and it's running, we need to inspect it and figure out where it is loaded. And fortunately, Linux allows you to do that using the procfs. We have used the procfs earlier to figure out the state of the binary, the state of the process. And now we will using the procfs, the process file system, again to figure out the memory addresses of different instructions and different segments of the binary. All right. But to inspect the procfs, we need the process ID of that process. So whenever you run this program that we wrote right here, this will not give you the process ID. We just will have the process running and it will quit. All right. But we need the memory address. We need the process ID. We need the process ID to actually inspect the procfs, because the procfs looks something like this. Cat proc, and here we need the process ID. And then to find out the memory addresses, we can go to maps. So if you cat this file, this will show you the memory addresses. All right. But to do that, we first need the process ID. So let's add So what we will do is, whenever we run a process with our debugger, we will print out its process ID. We were doing that, as you can see right here. We are doing that in this test process.c, but that is not true of all the program you're going to write. We did that in here, but you won't have that in all the programs that you write. So maybe if you add this line on every program in the main function, then you won't need what I'm going to do, but you're definitely going to need what I'm going to do. So what I will do is open nvim and then go to the attach function, the utils attach function that we have. So in here, whenever we, so this is in here, in this if case, we are attaching to external processes. But when we launch a process with our debugger, what I want to do is, I also want to print its process ID. So we need to figure out how to do that. So this is the program path, and we will already have that in here. So this process.launch actually returns a process object, right? Let process equal to, or does it return a result? It returns a result of a process and string. And if you see the process, you have the PID in here. So what we can do is, this will be a result, and if it launched successfully, then I will have the process ID in this process object. So if let error of e equal to process, in that case we have an error. I will simply return the error of e, but otherwise I know that let process, I can unwrap it. Process is equals to process dot unwrap, and I can print now launched process with PID, and I can print the process ID. Process dot PID, and this is a PID object, so I want it as raw, and that will be the int, and I can return a result of process. So return OK of, I don't even need return OK of process. So now when you run a binary with your debugger, it will print the process ID, and then you can inspect it, and we will do that. Let's try to run this binary that we have, this printer binary, with our debugger. So cargo run dot slash tests slash printer, and this prints the process ID. So now take this process ID, copy it, and go to another terminal. In here, cat slash proc slash the process ID slash maps. Let me increase the size a bit. And you see this. This is the address space of the current process that is running. So you see, these are the actual final addresses where the binary was loaded, and it is divided into segments. And you see this X here, this X means executable, and this implies that this memory block is where our executable binary is loaded into. This is the final memory block where it is. This is the address space, and this is where it is loaded. But every time you run that process, 5821 this time, so 5821, these memory addresses will be different every time. These memory addresses are randomized, right? And this randomization is there to prevent against malicious code injection. You have heard of SQL injection, and you can inject code as well. You can get remote process execution by injecting malicious code, but if this memory address is randomized every time, you won't be able to do that. And that's what Linux does. It randomizes this memory address space. But to test our debugger, to make our debugger work, we expect the memory address. We expect some memory address. All right. Now we want that memory address to be not random, so that our tests work identically every time. I want idempotency in my tests, and to do that, we need to remove this randomization right here. So we can do that for any process that we launch, but that is not possible for any process that you attach to. So if instead of running your debugger like this, if you pass in a process ID, you won't be able to randomize because the process is already running. How can you randomize it now? But if you launch a process through your debugger, you should be able to prevent that randomization. And that can be done again using a syscall. It's called the personality syscall. We need to run that personality syscall on the child process when we launch our debugger. So if you go into this launch function right here, so you have this is the parent process, right? And this is the child process. So before we exec the binary, where do we exec it? Before we exec into the binary that we for the new process, we want to remove the randomization in this process. And we can do that using the personality syscall. So this is where we need to add that personality syscall. So let's do that. We will do that before replacing the standard output. So right here, we need to call the personality syscall, and we will import it from, where do we need to import it from? I guess there is only one, personality. All right. And to this, we need to pass in a variant of enum, and that the variant that we want to stop the randomization is adder no randomize. And but this function expects an int, and so we need to convert this enum into that int. So as libc, whatever the c representation of this is, this will typecast it into that. And this returns a 0 or a 1. A 0 means there was some a negative 1 would represent that this function call resulted in some error. So we will check if it resulted in an error, and if so, we will process.exit. So if some error happened, we will write the error, let underscore equal to, we will write it to the parent process, right? Ampersand, sorry, write fd. We will write that failed to disable memory randomization, and as bytes, we will write it as bytes. That's what we've been doing so far. And then I can print an error, ePrint line failed to, same thing, disable memory randomization. The spelling is wrong here. Memory randomization, ePrint line, and then I can close the write fd. Write fd. and then we can exit out of the process with error status code, like so. So this will turn off the process, the memory address randomization. Let's see if we are able to still run it. Cargo run. Let's try to see the memory address space with 7743. 7743. All right. Now let's try to run it again. 7763 this time. And for both of them, I suppose now you can see that the memory address is no longer random. It's reproducible. So our tests could work now. Let's stop this. So we don't have a way to actually create a breakpoint right now. We have seen what addresses we need to apply the breakpoint to. We need to do some basic algebra over this memory address right here. So this address plus the memory offset that we had in, so where is that obj dump. So this is the relative memory address and this is the base memory address. So we can figure out the final memory address of each instruction now using this base memory address and this relative memory address. But we need a way to actually apply those breakpoints. So we need to create, so we have a CLI menu, right? So we will add some commands to our CLI to actually create the breakpoint. To add it to the CLI menu, find the dispatch command function, go to it, and we have the help and register command. So after the register command, I want you to add a breakpoint command. So else if breakpoint dot starts with a command, in that case we will add another command handler and we will add another function self dot handle. We don't have it right now, so breakpoint, and we will pass it the args self dot handle breakpoint. Handle breakpoint. All right, so we need to create this function. So let's do that. Let's copy this line because we need it. We need the parameter. We'll call it handle breakpoint. And in this, check the length of the args. So if the length of the args is less than 2, we want at least 2 arguments. So we'll check for it. If args dot, because we will set breakpoint set, breakpoint get, breakpoint remove or something like that. So the length should be at least 2 because we will have a command called breakpoint list and that will print all the breakpoints. So we need at least 2 arguments. One is breakpoint, the other is list. So if len is less than 2, in that case, we will call the self dot handle help, and to it we will pass the args, and then I will return. And we will need to update this handle help because we don't have the breakpoint menu here. So we'll add that later on. Uh, so the first command that we're going to add support is for breakpoint list, and we want it to print all the existing breakpoints right now. So let's get the sub command. Let sub command equal to args of 1. This indexing is safe because we checked the length. If list dot starts with sub command, in that case we need to get all the breakpoints. So we can check if current step points is empty or not. So if self dot stop points dot is empty, in that case we will print line no breakpoints set. Otherwise we will loop over it and print them. Print line, and we will print current breakpoints, and then instead of writing a loop, we will use the for each function that we created. Stop points dot for each breakpoint I will print line what are we going to print? So we'll print the address and the ID. We'll print two things for each breakpoint. It's address and ID. So so ID and address equal to, and we will print it in hexadecimal format. So that is hash x, and then we will also print if it is enabled or not. All right. So the arguments are going to be bp.id, then bp.address.adder, and if bp.is bp.is enabled, in that case the third argument is going to be a string called enabled, and then else disabled. Control comes here, and if that is the, then we can return from here. The other command that we want to add support for our breakpoint set, that will allow us to set at a virtual address. The next command would be breakpoint get by ID or virtual address, and then our commands are breakpoint. Let's not get them, we can list all the breakpoints we have already. So the other command we'll add support for are enable breakpoint enable by by the ID. So then breakpoint disable by the ID, and then breakpoint remove by the ID. So these are the commands that we want to add support for. What you can see is all of these require 3 arguments at least. So we'll check the length of args to be now 3. So let me just copy this. and instead of 2 it should be 3. So if set dot starts with sub command, uh, this takes virtual address, right? Yeah, we will do something. So we need, so the third thing will be the virtual address, but the virtual address will be received as a string, so we need to convert it to an integer. We have a function that does that, str to int, right? Yeah, but it's not public, so we will need to make it public. Right, control O. Let's use that function to uh, convert the address to an integer. Address, and it returns an option of, we'll convert it to a U64, str to int, and it's a generic function, so str to int, and we will convert it to a U64. The virtual address would be, we need to make it unsafe. Do we need to make it unsafe? Consider wrapping the function body in an unsafe block. Is this unsafe? No, it's not. Call to unsafe function handle register read is unsafe. Where are we calling handle register read here? Not. That's right here. I guess that's just the Rust analyzer fucking up. We'll try to compile it. Str to int, and the virtual address would be at args of 2, and the it will be converted radix 16, so it will be a hexadecimal string, and we will convert it to a U64. That's what this will do. And if it was not converted to the address correctly converted to an int, in that case dot is none. In that case, let's e print line and say breakpoint command expects address in hexadecimal. Breakpoint set command expects address in hexadecimal and return. Otherwise, we can create a virtual address out of this integer. Let virtual address equal to virtual address with adder, and we will pass in address dot unwrap, like so. Now we want to set a breakpoint at this. So write and space fw add. We don't have it, right? So what I'll do is I will create. So we are in process.rs, right? I will create a helper function that will add a breakpoint at a particular address. We don't have it right now. This will be U64. What's the error? Did not find commands in this scope. Dot start with. What else? Okay, there is one error. Here. needs to be command. So I will create a function that will be self dot add breakpoint at, and it will take a virtual adder, and let's say it returns a result, and it will return a result containing a reference to the breakpoint. So let bp res is equals to this, and if let OK of bp res, we will also enable the breakpoint bp dot enable. So before doing that, let's, because we do not have the help of the LSP right now because we don't have this function. So let's do that. Let's create this. Pub fn add breakpoint at, and it takes a mutable of self and an address of type virtual address, and it returns a result, and it will be containing a mutable reference to a breakpoint. Mutable because you want to enable it. Breakpoint, for error we will return a string. So in here, if we already have this breakpoint at this address, self dot stop points dot contains address, and this takes a reference to the virtual address. If that is the case, then we will return an error. Format, and in this I'll say breakpoint already set at address, and adder dot adder, and that's it. We will return it. But if that is not the case, we want to create a breakpoint. Let bp is equals to, now we have this function that creates a breakpoint, right? Create for process and at, so it needs a process. So self dot, and at will be the address, and we want to return a mutable reference, right? Self dot stop points, and I want to push into it. Push bp. What does push return? It returns a mutable reference. That's exactly what we want. Okay, so now we can come here, and now I want to enable it. So if let OK bp, not bp res, in that case bp dot enable, and the enable function takes a PID. So we need to get the PID out first. All right. Where, so let PID, it will be PID can be equal to self dot PID, basically, like so, and this self needs to be mutable right here. Let's try to write again. Bp dot enable, right? If let OK, but else we will print e print line breakpoint command expects address in if we were not able to add a breakpoint, so we'll just say not able to set breakpoint, and then we can return from here. That is the set command. The other commands that we want are breakpoint enable, breakpoint disable, and breakpoint remove by ID. So we want to first get the ID as well. So ID will also be received as a string, so we will need to convert it to a integer as well. So let's do that. Let ID and let's convert it to a usize. Usize, because the ID of a breakpoint is usize in our data type. In our struct str to int, and we will convert it to usize, and to it we will pass the args of 2, and it will be expected as a decimal, so we will pass in 10. So if now the ID is none, we will say that instead of hexadecimal we expect this to be in decimal, in base 10 basically. So if ID dot is none, eprint line BP ID expected as a decimal, and after printing that we can return because it didn't work. Otherwise, let ID equal to ID dot unwrap, and let so now we want to get the breakpoint at this ID. So let BP is equals to self dot stop points dot get by ID, and we will pass in the ID. But we want to enable and disable it, right? So that needs to be mutable. So this will be a mutable breakpoint. Now, if this breakpoint is none, that means the ID doesn't exist in our collection. So if BP dot is none, in that case, I can just say invalid ID. And then return. Otherwise, I can unwrap it, and so if the command given to us is now enable, disable, or remove, we will do each of those operations. If enable dot starts with the subcommand, in that case, let res equal to bp dot enable, and we have the pid, right? But self dot pid, I'm doing this self dot pid again because when we use that pid right here, this function, it actually takes the ownership of the pid, as you can see. So we need to get the pid again, because after this function call right here, this pid variable cannot be used again. So that's why I'm doing a self dot pid here. And if this led to an error, if let error of e equal to res of this, then let's just print whatever the error was. Eprint line. But if the command was not enable, if it was disable, then let me just copy it. Instead of enable, it is disable. Then instead of calling self.enable, we will call disable, and whatever the error was, it will be printed. And if, let's say, instead of so again paste and remove, if that is the subcommand, that what we will do is we will call the we want to remove this breakpoint. So what we'll do is self dot stop points dot remove by id. We have that, right? So we'll remove this breakpoint by its id. So it takes the id and the pid. So id is id and the pid is self dot pid, like so. And that should remove the breakpoint now. Let's see if this compiles correctly. Cargo build. It does. Okay. So now we have added all the commands that we need to our CLI menu, but we would also need to update the function that prints the CLI menu. We have this handle help function, right? So since it's going to get large, I will create helper functions for this as well. Uh, So if args.len is this, what I'll do is I will create a function and I'll copy paste some functions, and I recommend that you do so as well. Remove these 3 lines. Self dot print general help, and otherwise in here we want command specific help, right? So we will create another function that will print command help. Self dot print command help, and it will take the specific command. Now we need to create these 2 functions, this general help and the command help, and I will copy paste these, and I recommend that you do so as well. Let me bring that code in. So these are the 2 functions that I need you to copy and paste. In the general help, we will print all the commands that we are helping with. That is the continue, register, breakpoint, and the help command. And in the print command help function, we will print help for specific commands. So for register, we will say that we have the register read command that shows all the registers. Register read all does the same thing. Register read given the specific register name will print the value of that register, of that specific register, and this register write will take the register name and the value that needs to be written. So the examples are register read rax and write with register write rip and the value in hexadecimal. Then we have the breakpoint command. We have the following commands: breakpoint list, this list all breakpoints; breakpoint set at a specific address, it set breakpoint at address; breakpoint enable, it enables the breakpoint by the id; disable the breakpoint, and we have not delete but remove. So it removes a breakpoint given the id, like so. The examples are breakpoint set hexadecimal value, enable, remove, and the id. And then the continue command, it resumes the execution of the debugging process. That's it. These are the 3 commands that we have right now. We will add more soon. Let's see if it builds. Should. Alright, it does. I guess that's it for this video. We will try to add breakpoints and stop the execution of the debugging process in the next video. That's more or less the code that you need to enable and disable breakpoints. Anyways, I'll see you guys in the next one.